maybe someone should stay there and check in the Zoom session equations and so on. I don't know who's in chair of the seminar.
Oh, okay, so I could share it.
And if you can,
And if
I will was chair.
are you Marek?
No, Marek is not here. Maybe he will come. I don't know. But typically, someone stays there and checks because, especially after the session, people might ask why is Zoom
Oh,
recorded.
okay.
And maybe you could check with the people here.
Then I look at it.
I'm going to set a timer for 25 minutes. So once one of my talk is finished, I can switch over to the other one. So just a reminder. So I'm sorry if it's going to start making noise during the. Do people stand up here or do they go down there?
You can stay there. I think it's better for the video.
Oh, I see. People can look up as well.
I think the camera will follow you.
Okay. Oh, this is a camera is following me.
Yeah, it should at least.
Or at least the face.
That's cool. I like technology. Ez az enyém.
Ezen van a Zoom?
Igen, van.
De hogy térdeltették rá
Én is használok Zoom-ot, szerintem az van, hogy azon keresztül elküldjük a linket, és úgy lett megosztva.
Ja, értem.
És szerintem kap internetet, igazán ezen keresztül minden van. Már elindult, azt hiszem az Zoom-et.
Néha haradok, hogy valami.
Most nem látom az Zoom-ot, az előbb itt volt. Én nem tudom, mit csináltak, hívuzték a oldalra valahogy. De vagyunk jelentkezve, biztos vagyunk beszélni. Prezentálni. Hello? Szerintem ez rossz telefon. Köszönöm.
Tehát most megy az umor minden.
Okay, are you ready?
Ez a kérdésem, igen.
Yeah, I think so. We are presenting that it's this presentation mode, so that means is that it's sharing the presentation. So I'm just going to just a second, it looks like.
Yes.
And I'm ready to go.
Köszönjük.
Thank you for coming, for all of you. My name is Viktor Chikan. I'm a professor at Geza State University, and I also work overseas here at Extreme Light Infrastructure in Hungary. So I'm going to give you two brief talks. It's a salad bar. So I'm going to talk about the research I'm doing at Kansas State University, and a very different research, and also research opportunity for some of you at this user facility. So Kansas State University has this nice building, and that's why I put this thing on my slides. My research interest is synthesis and spectroscopy characterization of nanoparticles, magnetic hypothermia, and chemical dynamics. It's quite diverse set of experiments, but let me see. It looks like this thing died. Well, let me see if this is going to work. I think my presentation tool just died.
Lehet, hogy át kell kattintani, nem? Lehet, hogy én szóltam azért. Lehet, hogy elvesztette a fókuszt.
Yeah. Now it's working. Okay, so my research interest is looking at nanoparticles and how magnetic nanoparticles can be used to trigger a biological response. And so, this idea that using a remote control to do this is something that's been an interest of mine from a methodological perspective. And it started when we started looking at this effect of magnetic hypothermia. The magnetic hypothermia is a process when you take these magnetic particles, you put them into the alternating magnetic fields, and then they can generate heat. And people use this for cancer therapy, kill cancer. And there are two different mechanisms. One is the Brownian relaxation, when the entire particle rotates in the alternating magnetic field and creates friction and heat, or the magnetic moments realign in the particles. That's for smaller particles. It's called the Neal relaxation, and that generates heat as well. So both processes are an efficient way to generate heat. The problem that came with this is that, when you generate heat and you want to treat cancer, you need a lot of nanoparticles. You need a few milligrams of these nanoparticles per cubic milliliter of cancer tissue. And so it's not very effective. So and also generating heat means that the entire matrix has to be heated up, not just, when you want to kill cancer, you want to do this like a more strategic way to take that magnetic field energy and put it in some way that will have the same biological response. So, we've been using, these inductive heaters. You can see that generates alternating magnetic field, a sinusoidal small amplitude magnetic field. You can melt a screwdriver in about 3 seconds, which melts at 1600 degrees Celsius. And then you can boil nanoparticles as well. And so we use this for cancer therapy, melanoma cancer in mouse and pancreatic cancer. But so this was based on heat. So what we wanted to do is, instead of generating heat, we want to create mechanical energy that will have the same impact. And so to do that, we need a higher magnetic field. So what we did is, instead of using these inductive heaters where you have a sinusoidal alternating current going through these coils continuously to make that magnetic field, we can achieve these higher magnetic fields using pulsed delivery systems. When we use short pulses of currents, putting 40,000 or 50,000 amps through a coil for a very short amount of time, and we can create these very high magnetic fields. And I'm talking about magnetic fields about 1,000 times larger than what you would get in the inductive heater. And so the idea is that instead of continuously operating the magnetic fields, we do that in a pulse modes, and in each pulse you actually get more power. And so the magnetic pulse looks something like this, an underdamped oscillation essentially, and we can create these beautiful magnetic fields inside these electromagnetic coils. These are simulations. This is two different types of coils. If you've heard about the term Helmholtz coil, the idea is that you have a loop, an electromagnet, and if you put two together in the right way, you can create homogeneous magnetic fields inside. If you remember your physics, then now if you can flip around the one of the magnet and then you can create this so-called anti-Helmholtz coil, where you create not homogeneous magnetic fields, but the opposite, inhomogeneous magnetic fields. And so we can study effects both of these in these coils. So we have a power source. We can push 40,000 amps through these coils, and we can look at how it affects the different particles. We can also create rotating magnetic fields, which is when we take two of these Helmholtz coils and we stack them 90 degrees. We can add up two sine waves in the right phase, then it will create a rotating magnetic field that will go in a circle, as it's shown here is probably, okay? So the idea is that you can create an electric drill essentially with the nanoparticle kind of rotating. The other fields, I will talk a little bit more about that. It's kind of important, and so I just want to show you a model system, how we can do this, so in a practical term. So the idea is that, for example, we can take liposomes. These are consist of phospholipids and cholesterol. These are stable packages where you can put stuff inside of them, and they are stable in biological systems. They are widely used, to deliver drugs, cancer drugs, and any other kind of drugs in humans. But the problem is that these liposomes are not very easily actuated. Slowly they diffuse the drug out from these. There are different actuation mechanisms that people can use, like lasers, ultrasounds, and so on. But the time scale that you do that is relatively slow, and we wanted to improve that. So what we did is we put drugs and magnetic nanoparticles as the actuators inside these liposomes. And we wanted to expose these liposomes to magnetic fields to release the drug. So the idea, very simple. We have the actuator, we have the drug, we have the liposome, we apply the magnetic fields, and this stuff comes out. Very simple. And we can do the same thing with cells as well, but so the liposomes are kind of a model system. So I'm developing methodology that will be used for cells. And so we have a dye. We can look at the dye as a metric, how efficient our drug delivery. So I'm not going to talk too much about I don't have the time for the analytical part of this, but basically we can analyze the amount of drug that comes out, and we can focus on the efficiency of drug delivery. So if we don't have good efficiency, 0%, if we have a single pulse applied and completely comes out, it's 100%. So I can tell that based on the chemistry we use. So, but what's the mechanism? So it turns out in inhomogeneous magnetic fields, when you apply these magnetic pulses, here's the magnetic field, or it's actually that shows like this. And then, if I put a microphone inside a solution of magnetic nanoparticles, which is called a hydrophone, you can actually see the sound waves that's coming off from these nanoparticles, as you can see it. And then more nanoparticles you use, you get more of this as, this peaks is growing in. This is the Fourier transform of this time domain signal. And so there are two different mechanisms for the ultrasound generation. One is the shape change of the nanoparticles. When you apply magnetic fields, you just need a large magnetic field, and this is called the magnetostriction effect, and it creates these vibrations inside the solutions. The other is the effect that you have inhomogeneous magnetic fields all the time in these magnets, and that can make the magnetic dipole move in these inhomogeneous magnetic fields. It turns out that this inhomogeneous magnetic field is very important, and I will show you some data. So we demonstrated this. We have a few papers on this. We can put the nanoparticles inside and outside. So the actuator or trigger doesn't have to be inside or outside. And there's some advantage to put the drug or the nanoparticles outside. We can put more drugs inside, so it's more efficient. And we can do the nanoparticles, add them, later on in the post-synthetic methods. So we make the liposomes first, and then we add the nanoparticles, which I didn't talk too much about how we make the liposomes, but I apologize for that. But it's a standard technology. You can actually see these liposomes when we put the nanoparticles outside. So these are these phospholipid vesicles with the drug inside these, and these black things are the nanoparticles and they stick to the surface. We're going to attach them to using gold iron magnetic nanoparticles, and we use thiochemistry, thiolated cholesterol, which makes up the phospholipid to make a surface sticky, essentially. So that's a methodology we have developed. Now, one of the things that we do is, we do actuation of these liposomes, and other people made magnetic liposomes before. We were not the first one, but they used magnetic hypothermia, the process earlier, to trigger these liposomes. And when you look at their time scale, they release the drugs very slowly on the time of minutes. We apply 200 microsecond pulses. So per unit time, actually, we can release way faster than anybody else in the world with this methodology. So when I basically look at the unit time release per percentages, these are some papers that we got from the literature, and then you can look this up. And this is our work. This is one of our work. We have several papers on this now. DPPC with iron platinum nanoparticles. It's almost 6, 7, 8 orders of magnitude faster than what other people can do. So this is useful when you put the liposomes inside the human body. You have a magnet, you trigger it, and then you want to have the drug released locally, as opposed to you slowly doing that and kind of diffusing through the body, or so that, or you have a drug that it's very short-lived. It's not very effective. So this technology is basically expanding the capabilities of liposome research. So we can actually apply this same methodology for cancer therapy, which is what I started out with in my talk, is instead of getting drugs out from a package, we can get drugs into the cancer cells. So the idea, this methodology we call it's a Trojan horde approach. We feed the cancer cells with magnetic nanoparticles that are sugar-coated or dextrin-coated. So because of the high metabolism rate of these cells, they go after the magnetic nanoparticles, so they digest it. Once the nanoparticles are inside, we can add drugs outside and then look at, what would happen with the cells when we apply these magnetic fields. And then we can open the gates, essentially, once the Trojan horse is inside the magnetic nanoparticles, we can apply the magnetic fields and shake these particles. This is actually some work that we have done, and we have a patent on this now. That so we have these cells, U937 cells. We show that you can add the nanoparticles. This is a microscope images of with and without iron nanoparticles. The iron is this can be stained with the Prussian blue, which gives you the blue color on the microscope. And we also have TM images that shows that nanoparticles go inside these cells. And so once they are inside, we put doxorubicin outside. So the cell we look at, how so-called the IC50 curve. So somebody works in this biological field. So that means is that, the critical concentration of the drug that's needed to kill 50% of the cells. And so we look at, how this IC50 curve is affected by the presence of the magnetic fields and magnetic nanoparticles. And we do see a significant increase when we use the nanoparticles and doxorubicin and we turn on the magnetic fields. So this IC50, the 50%, that's, there's a large jump. There's a significant increase. Then we do also analysis of how much more drug we got inside the cells. So you can take apart the cells after you have done this and use an HPLC study, chemical analysis, essentially the drug. And we see a 70%, 75% increase of the doxorubicin inside. So this was a paper that came out. We've shown that this works not only with the U937 cancer cell line, but the other cancer cell lines. It works also with different drugs. So this is a methodology. It's not unique to this particular system, but basically it can work for any cells or any types of drugs. So this is my, I was actually going a little bit fast, but this is an exciting research. So the idea that using mechanical energy to create micropores on lipid bilayers, that's something that intrigued me. And then going back in the future, what we might do is, do more of this rotating magnetic field. So the fields, magnetic fields, we use this inhomogeneous magnetic fields. It creates that vibration. So you shake these cells or liposomes, you have the pores, and you can get the drug coming and going. It's great, but we ultimately want to have things like, let's say, put a nanoparticle to the lipid bilayer and start rotating it, actually drilling these liposomes. For that, we need these magnetic fields. So this is something that we might do in the future. So we have the tool for that. We haven't demonstrated anything with rotating magnetic fields yet. So this is just kind of the next step, next phase of the development. We have also found, I don't have that results here, unfortunately. The magnetic field dependence of the drug delivery very nicely. We can correlate with the different types of magnetic fields. You're writing a paper, so if you have time, look for that, once it comes out. So this is the first part of my talk, and I'm gonna switch over to my other talk. And we have to share this, reshare this, probably the screen one side over to this part. So I go here. And we're gonna say share. Yeah. I hope you can see the same thing as I do, right? I think that, yeah. All right, so the next thing I'm going to talk about is the project I started in 2014 when I did my sabbatical overseas at the University of Szeged. I got involved with this research facility called Extreme Light Infrastructure. And I want to tell you a little bit about this because it might have relevance to you and to your research interest. It's a laser facility, and it's one of the first of this kind. Oh man, so I think if I remove this to be engaged again. Here we go. The U.S. Department of State paying me, to be here for this summer through this Fulbright Scholarship, and this is a named scholarship called the John von Neumann Distinguished Award. And so I need to talk a little bit about this, just a little bit. Von Neumann was a famous scientist and mathematician, essentially, and formulated the ideas that was necessary to create the first computer. So if you have a little bit of time to read about this gentleman, please do so. One day, maybe, somebody's going to be reading about you, the same. So, but anyhow, I'm grateful. So the Eli is located at University of Szeged. There's a university there, University of Szeged. But it's actually at 3 different locations, one in Prague and one in Bucharest. So it's more a network of large scale facilities. And Eli in Szeged focuses on attosecond spectroscopy, higher harmonic generation, and to making XUV and these pulses, but it's also making all kinds of light pulses that can be used for experiments. Here are the colleagues. Gerard Moreau got his Nobel Prize in 2018. He's considered the father of the Eli. He's basically created the technological improvement necessary for the creation of this facility, which is the pulse amplification. And this is our group there. So Eli feels in a need in spectroscopy and laser physics, to be able to do experiments in certain range. So if I look at photon energy and peak brightness, Eli can be found somewhere here. And these are other facilities in the world that, cover this graph. And the idea that how it works, that you have large lasers at this facility, and there's a delivery line, and there's end stations or secondary sources that can be generated from the primary source. And many times these lasers, they only produce a certain wavelength, and then you have to convert it to different wavelengths or different characteristics. And there are user experiments, and this is where you can participate, where there are different end stations where you can do different kinds of science with these lasers. My group is responsible for doing transient absorption spectroscopy, pump probe experiments in the condensed phase and the gas phase. And so as far as the layout of the facility, you can see this is like a large optical table with lots of lasers. The lasers are located at different places, and you can see this, these different labels indicate the different types of lasers. Just like a salad bar again. You go and look at the different types, what you really need, and then they also serve, the secondary sources as well. Our experiment, which is, the transient absorption spectroscopy, is located at the right here, which is the HR1 and HR2 laser system. It's a 100 kilohertz laser system. They are very cool, very short light pulses, CP stabilized, and very high pulse energies, which is great. The high rep rate is great also because statistically we can do very sensitive pump probe experiments, and the transient absorption setup is located there. We also have another experiments, a chemical reaction. I'm not sure, I'm lost here, but basically the silos 2, there's another chamber that we're going to be talking about here. But there are lots of experimental stations. So there are 5 experimental stations that are user operational. There will be 12 altogether, and you can go to the website. There's a way to submit a proposal. A proposal is a one-page thing. You put your science there, what you need, and it will they send it out for peer review. Once you receive a favorable response, then you can do your experiments. Either you send your sample or you go in person and you do the experiments, and resources are allocated for that. So I highly encourage you to do that. And please feel free to contact me if you need any help with this. But there's some examples, VMI, REMI, people who work on this, they don't know what this is. And I just mentioned these names, but there are also positions open at TILA, if you want to work overseas. So our experiments is transient absorption spectroscopy. So this is, where my group participates, and Christina is here, from my group, she's doing a PhD with me. We built this experimental setup to do pump probe spectroscopy, where we can, for example, look at the excited state dynamics of molecular systems or nanosystems in the condensed phase. And so it looks like a complicated box, but it's really, basically it's a high-speed photography of looking at, these dynamics. So this shows, some picture of that. The cool thing about our experiment, for example, we can look at exciton dynamics. This is molybdenum sulfide material, and this is just a test experiment just to demonstrate to you that how this works. We can excite the exciton. We can see the AB exciton of the molybdenum sulfide, and it goes away quickly. We can learn about how it can be influenced. And this is the type of information we provide to users. We can do this in reflection mode or transient or transmission mode. We can combine these transient absorption spectroscopy technique with other techniques. So that's our other unique contribution. We can do electrochemical measurements where the sample is electrochemically biased, for example. These are important for liquid solid interfaces. Or solar cells and things like that, and you can bias and look at how the exciton dynamics is changing. So this is a transient spectral electrochemistry. The other thing we can do is we can actually look at transient absorption spectroscopy of molecular systems or nanosystems that are evolving over time. So one of the things that this transient absorption spectroscopy does, we can learn about dynamics at very fast time scales, because we have very fast lasers, and we are talking about femtosecond time scales with this particular setup. But we can also do the experiments, these transient absorption spectroscopy so fast with these 100 kHz laser systems that we can learn about the chemical evolution of the system and how these dynamics are changing, which is an in situ experiments. It provides a new sets of information, which is not possible otherwise. So it's a methodology. I know I didn't show you too much of the science, but there's lots of possibilities, and I can tell you, I actually have plenty of time here, so I can talk about this. I don't want to rush here. So technically, the way that we can do this, there are 2 things you need. First of all, you need to be able to detect the light very, very rapidly. So we use methodologies. We developed our methodologies to do that. And so one is called so-called lock-in detection. Lock-in detection in physical chemistry is a detection method when you have a large signal and you try to detect a small signal. So you modulate the signal to do that. And so with spectrometer, it's difficult to do that because the spectrometers were very slow in the past. But now we can get these very fast spectrometers, and we can synchronize with the mechanical choppers to be able to extract that information. Alternatively, we can actually use 2 spectrometers at the same time, so we can measure the light before and after the sample. So in this way, we can, if there is any fluctuation in a light, we can factor this out, and we can focus on the changes induced by a pump pulse in the pump probe spectroscopic setup. So these are very fast. The 100 kilohertz laser system basically ensures that the theoretical limit, what we can do right now, and maybe in a few microseconds, we can actually take a transient signal from this sample. So this is extremely fast. And so the other thing we need is, we have a mechanical delay stage to create the pump probe setup. So people who work on, pump or heard about pump probe spectroscopy, it's basically done that you have these pulsed light sources and you delay the one pulse with respect to others by making the light going in a longer path length. So these mechanical delay stages are very slow because they have to mechanically move. So one of the things that can be done is instead of using delay stages, you can use two laser systems that are, they have the similar rep rate, but not exactly the same. And so this is called the asynchronous sampling. And so the two laser systems with respect to one each other will continuously getting a delay with respect to each other. So you can electronically detect this. And this requires no mechanical delay stage. It requires two laser systems and electronics to detect well, to tell where the pulses are. So this eliminates, this delay time. So, and so that would be, we will be able to push the limits of this transient absorption spectroscopy, where we can take this data very, very rapidly, okay? And so if I go back to the picture here, the idea is that, when we look at this femtosecond dynamics, can I be connected back to slower time scales where nanosecond, microsecond, or millisecond evolution of the chemical systems happens. So we're talking about chemical reactions as they happen and how it impacts the dynamics of system. For example, I give you a couple of examples. So right now we are looking at the evolution of gold nanoparticles in solutions, and then how the transient absorption provides additional information of that, the evolution of these gold nanoparticles. Second, we look at another system, let's say doped quantum dots, where we want to do the experiments at high temperature, so we can see the ionization of the dopants, and transient absorption provides you information about exciton lifetimes. So these are two things. So the gold nanoparticle system, so we can make these gold nanoparticles inside the reactor while we are doing this. And so the gold nanoparticle has a very short transient absorption lifetime. It's a plasmonic material, a few picoseconds, 3-4 picoseconds, it relaxes. But on top of that, it also has acoustic modes. As you know, all this energy goes into the particles. This breathing mode results in a modulation of this transient absorption signal. As you can see it here, these oscillations are real. Okay, it turns out that this oscillation is very sensitive to the size of the particles. And so what we can show, as these particles are growing, this frequency is changing inside the solution. So now, all of a sudden, transient absorption, we can watch the particles growing. You're not going to be able to see this information unless you put an electron microscope into the hot solution. So now with transient absorption, we can actually see this information and learn about the chemistry of these nanoparticles and how they form and what influences their growth. So this is a cool project, and so I can see people might be interested in this, and the user experiments. And so if you have a chemical system that's where you want to look at exciton lifetimes, for example, like quantum dots, semiconductor quantum dots, or you have a molecular system, you want to look at the excited state and what happens with this excited state under certain conditions, let's say oxidation reduction or some kind of process. This is an opportunity to be able to do the experiment. So we have the capacity and the capability to do so. And our job is to serve users, so the stuff that I'm showing you is really just a demonstration experiments, the capabilities of these instruments. And so that's part of the reason of my visit, and very grateful for Geza for this opportunity here. So let me tell you all about the second experimental setup that we've been working on, and Fulbright gave this, it looks like my remote died again. Maybe I walked too far. Yeah, let's see. So the second experimental setup we are working on, and this is what Fulbright gave me the money for, is to look at pump probe experiments in the gas phase. And in the past, about 20 years ago, or 15, 20 years ago, I worked on a methodology at the synchrotron light source, at Advanced Light Source in Berkeley, where we looked at how synchrotron radiation can create these radicals, and developed a methodology called the Fourier transform visible spectroscopy to look at the fragments. And so I wanted to implement this for ultrafast lasers, at Eli, to provide additional information. So the idea is that we have a vacuum chamber. We can blow up molecules with an XUV pulse, or we can focus infrared ultrafast lasers to do Coulombic explosion experiments in this gas chamber. And then the fluorescent fragments that we produce carry some of the energy from the laser pulses, and we can image that on a spectrometer. And the spectrometer can provide us valuable information about how these molecules are picking up the energy from the dissociation processes. And this is relevant to figure out how the molecule falls apart. Where does the energy go? And then we back calculate, we look at the experiments and try to figure out, what's happening inside the molecule when this dissociation happens. The dissociation can be initiated, as I mentioned, with XUV pulses. XUV pulses are very high energy pulses that enough, to break chemical bonds. We need this high energy also when we add this energy, that the fragments will have enough energy that produce fluorescence fragments as well. So it provides a fingerprint about what's going on. So we can chemically identify the products. We can also look at, how hot these products, and we are not talking about thermal equilibrium here. There's no thermal equilibrium when you do these experiments. The energy starts flowing according to quantum mechanical rules, so that's what we're trying to be playing quantum mechanics here. And we want to figure out, where that energy goes and what determines that. And so a little bit about this methodology, we use this Fourier transform technique, which is a Fourier transform technique. It requires a Michelson interferometer. It's widely used for in FTIRs, infrared regimes, to detect chemicals and that sort of stuff. So the way we do is we use it in a visible spectrum, so which requires a little bit better interferometer than what's used because of the shortness of the time. And we can, when you have this Michelson interferometer, we can actually stop the interferometer at different points, and we can do time-resolved experiments as well. So we have a fluorescent fragment because we use pulsed lasers and they decay. And each point in the interferometer, we can take these decay curves. So we can actually get a two-dimensional spectrum. One dimension, you will have time information. The other, we have the frequency information. And so, so when we create these two-dimensional interferograms, we Fourier transform, and you get the two-dimensional spectrum and the time. So time-resolved spectra. So if I want to keep it simple. So this is, we can also do pump probe experiments in the vacuum chamber. I said that, we can do photodissociation with probe fluorescence, but what if we're going to have another pulse coming in and we start manipulating these molecules before they do the photodissociation? For example, we can align the molecules. If we use a very strong electric field pulse called terahertz pulse, then we're going to be able to align the molecules prior to that photodissociation. So these aligned molecules will react differently than unaligned molecules where you have randomly distributed molecules. We can also do things that apply electric fields when the photodissociation happens. So we have these terahertz pulses that we bias, create an electric field bias of the molecule, and then we have a photodissociating pulse, and the effect of that first pod can be measured. Okay, so this is a cool pump probe technique. So from the detection side. So what does this terahertz field does. So let's talk about a little bit this. So because that's, I think, it's cool. So terahertz is terahertz means essentially 10 to the 12 hertz. Okay, so that's the frequency regime, but it's far infrared if you think about this, or microwave. And so it turns out that in this regime, the frequency is such a low frequency that, well, such a slow electric field that it's not resonantly exciting anything in the molecule. Okay, and so this is if you choose the right molecule, of course. And so it's a quasi-static electric field. Okay, and then when you start increasing the intensity of this quasi-static electric field, we can do Stark spectroscopy. So Stark spectroscopy is the idea that you use an electric field and you look at how the molecules behave in these fields. It's a spectroscopic technique. People use that in all times. Using two plates that they put the electric field, and then they look at the polarization effects, for example, of these molecules. We can do a similar thing, but we do this with pulses, light pulses, terahertz electric pulses that looks like this. And these high intensity fields are much larger than you can achieve with two electric plates. So we can go up to a few hundred, even mega volt per centimeter electric fields. And that's getting comparable to the basically interaction of the Coulomb interactions of the atoms inside the molecules. So this provides, a new opportunity to look at, how these molecules behave. So one of the things we can do is, so the terahertz field can control these reactions through alignment. So people use optical pulse to align pulses, but these are not orientational. So terahertz pulse, because it impacts the dipole, it would orient it in a certain way. This has been demonstrated by other groups. We can provide optical bias during photodissociation, and that would be interesting. Influence, for example, curve crossing in the dissociation pathways. So if you have this curve crossing on this high excited state, you can tell, you can push the reaction in different directions. You can also modulate barrier heights where you have tunneling processes, so quantum magnetic tunneling, by adding an additional bias that will influence these reactions. So what we measure is energy disposal. Here's this, idea of modulating the product using these electric fields. This is a calculation paper that came out a few years. It hasn't been demonstrated, okay? So we are talking about science that, we want to do experimentally. Theoreticians predicted, but, the experimental is just becoming real. This is the dissociation of ammonia, NH3. You apply a pulse, and then this theoretical paper investigates the excited state influence, and this is the there's a crossing here in these two surfaces, okay, and then when you apply this electric field, it's very sensitive. This crossing is very sensitive to this electric field, and when the molecule starts dissociating, it will determine how much of the NH2 A state versus the X state you produce, the ground state and the excited state. So they've shown that, applying, these reasonably large electric fields, then, you can actually do this. And so the idea of using light or terahertz fields to control chemical reactions is intriguing to some of the people. And so it's a little bit simpler way than coherent control, if you've heard this expression. And people use laser pulses to do that, because we wouldn't do this with a laser. We would use a terahertz pulse, which is from a laser, but it's not a coherent control way. It's a different way to control these chemical reactions. And so the probe system, I need to tell you about how this machinery works a little bit, and so I want to give you a little bit more detail. So we blow up molecules, and we have a molecular fragment, And so one example of this, the CN radical. CN is extremely stable radical. You can detect in outer space as well. There are many electronic states. For example, the B state here is the B to X transition. This is something very sensitively. You can see it in the UV. So you have these many electronic states, and you see these very large peaks. We use the technique to obtain the rotational and vibrational energy distribution of this fragment. And so when we resolve this is with a low resolution spectrometer. We resolve this, we can see these peaks. You can see the vibrational modes and the population from the photodissociation. Let me see if how much time I have. I have 2 minutes. So we have, usually what we do is if we focus this, this is a column explosion experiment, and we can put different chemicals here in different carrier gases. So we can differentiate between reaction that's coming from the primary photodissociation versus the secondary reactions where the buffer gas reacts with the molecules that we produce. That's why we need a time-resolved machine. So when I said time-resolved methodologies, if you go back here, early on, we talked about this Fourier transform time-resolved setup when we take two-dimensional interferograms. This is necessary in order to take this time-resolved data, and so we can differentiate. The secondary products will come later, the primary products that emerge from the primary photodissociation. So we cannot stop the collisions of the molecules once you produce. The fluorescence takes a long time, the fluorescence photons comes, and so we can differentiate the different types of photons when they come, and in this way we can detect the actual chemical reactions and the energy disposal of these molecules. And so we do low resolution scans, and when we go high resolution, so this is the type of experiment you see, we can measure spectra with 0.06 centimeter minus 1. So this kind of limits the type of molecules we can look at. And we do this in the jet-cooled molecules. So we cool it down with through adiabatic expansion of the molecules before we blow them up. And so these diagrams are showing a nanosecond scale of the spectrum. So we take the spectrum very, very rapidly. And on the graph, I also show you the collisions. At this pressure, we can calculate how many collisions we can have. We're looking for the spectra that happens before any collisions. And that will tell you the energy disposal of the molecule right after photodissociation and how the energy is distributed. And we can infer something from the dynamics. And so what we do at this point is that when we get this beautiful spectra, as you can see, it's very beautiful, molecular spectroscopy, we can actually fit it with Boltzmann distribution of rotational and vibrational levels. So we get different temperatures. You can see that the rotational temperature and the vibrational temperatures are not the same. That's one thing. We have an assumption that there's a thermal equilibrium, which is not the case here, but for simplicity, not to confuse you, we are assuming that there's some energy distribution. So when I say temperature here, it's really meaningless because there's no thermal equilibrium, okay? But it gives you an idea about how much hot in different parts of the spectrum. For example, at 10 nanosecond, you can see that the temperature, rotational temperature is about 8,000 Kelvin. And after 200 nanoseconds, the same molecule, just a little bit coming late, it's only 1,000 Kelvin. That's due to the collisions, so basically energy starts flowing into the collisions. But in these high temperatures, and you can see there's more temperature and rotation in the vibrational, that tells you something about dynamics, how the molecule falls apart. So it's not even, so there's more energy goes into rotation and vibration from the photodissociation itself. So we use this information to detect the dissociation dynamics. And in the pump probe experiments, when we do the terahertz experiments later on, we can look at how this is changing. So this system, this sophisticated experimental methodology, it tells you something about the dynamics, and we can look at the influence of other fields, what would happen. And that's, we can figure out how the molecule actually works inside. So this is, and for those of you who do, quantum mechanical calculations, basically all of this that we measure, it comes out all from these quantum states and what the electrons are doing inside the molecules. And we want to understand the rules that drive this, these things that we provide experimental data. Just to, give you some more graph, and I'm going to finish up probably soon. We can actually plot these, temperatures as a function of time, and then you can see where the transition happens. So we're going to the any time equals 0 time. This is where the photodissociation happens. This is called the nascent energy distribution. Nascent because it's after birth. That's what this means. After birth of these molecules, where the energy goes, and that's the information. We don't want to have any collisions with other molecules. But if you want to look at how the reactions happen after we create these highly excited states, we can also watch that, and then we can look at the energy flow. So this is an experimental opportunity for you as well if you are, want to do ultra-fast science in the gas phase. And you can actually see the jet-cooled molecules here glowing once you hit with the laser. All these fluorescence fragments in the adiabatic expansion you can see. We can probe different parts of this adiabatic expansion as well. How cold the molecules, they're going to have different energy distribution. So it's a beautiful results. So one of the things we're looking at is that I haven't told you, in Coulomb explosions, the primary products are usually ions. And these ions are very easily detected with mass spectrometric techniques, and there are lots of groups that are doing that. Our unique contribution is that we're looking at the neutral products. So the fluorescence fragments that we observe are usually radicals, and this provides a new information about just the neutrals, and which is unusual thing, when you do a Coulomb explosion, experiments with high intensity ultrafast lasers where the electrons are stripped off from the molecules and you mostly produce ions, but there are some neutral fragments that are produced and we are watching them. Okay, we can tell when different types of molecules, whether they produce neutrals and how efficient those production channels are, which tells you something about the mechanism as well, of these Coulomb explosions. So I think it's an extremely exciting opportunity for experimentalists to look at some slice of these Coulomb explosion experiments with this particular methodology. So anyhow, thank you for your attention. I know that I've given you lots of information, very little justification, for some of the ideas that I presented, but I just want to engage with you on this, and hopefully I can answer your questions or, give you some inputs, if something you found interesting. So thank you very much.
So actually, we have one question on the internet, and afterwards I ask the audience. So Alexander Bittner asks, one of the many problems of actual magnetic hyperthermia therapy is that the oscillating magnetic fields induce currents in the patient's skin. This means the magnetic flux and frequency have much lower limits than in experiments with cells, and in turn, the magnetic nanoparticles must have a very high SAR. Should pulsed fields not be even worse for patients, especially with such strong fields?
Oh, excellent question, and I think it's just let me just rephrase the question what the gentleman is asking, because other people might not know. The question refers to what happens when you take these magnetic nanoparticles into low magnetic fields and you start heating them. Then the magnetic field itself will induce currents, and its influences in the effect is itself. And so in order to make the heating effective, the nanoparticles has to have this heating efficiency very high to be able to deposit energy quicker into the cancer than to the rest of the body. Okay, so it's a contrast issue. So first of all, the mechanism is different for the SARS, the magnetic hypothermia versus the mechanical. So it's one creates vibrations, very short amount of time, the other creates heat. So there's no heating effect, in the pulse magnetic fields. Now we have issues with the it can polarize, the lipid bilayers. There are people did high magnetic field experiments on lipid bilayers. It does that. You can trigger nerve cells, with pulse magnetic fields. So there was an experiment that people demonstrated that when you use pulse magnetic fields, you can restart the heart of a dog that was stopped. And so, this is significantly impacting the body, but it's very sensitive to the types of the magnetic field amplitude and frequency of use. So in our experiments, it's a different types of experiments. But it still has a frequency, and depending on the frequency and the magnitude, it can do the same thing, but it can be avoided. So it's not necessary that it would cause a problem. As far as heating goes, the high intensity magnetic fields have very minimal heating. So that's something we measured. So when we did the cell experiments, we put a fiber optic temperature sensor, put it into the magnet, and then measure the temperature of the solution. We don't see any heat increase. It's not observable. That's because the magnetic field only present for 200 microseconds. So you make the mechanical energy. The mechanical energy, although it's very, very intense, but the buffer is very large. So the human body, we use very little nanoparticles. The human body is huge compared to the nanoparticles and the mechanical energy that needs to be converted to heat. And so effectively, there is no increase in the temperature. So temperature increase is not a problem for this methodology, I can say that.
Thank you very much. Other questions?
Yes, sir.
Yeah, you focused primarily in the second part here on your actual experiments and what is interesting, but could you tie it a little bit back to the actual facility? Because it wasn't that clear to me what is possible now with the new facility and that wouldn't be possible in any other laboratory.
Yes, so there are laser systems in other laboratories, right? So the thing is the limits that we are pushing. So so this laser facility provides shorter pulses for users. So I know that there are laser facilities that they can make 4 femtosecond pulses or 3 and look at dynamics, but it's only available for one group. This facility provides at the industrial scale, basically experimental use that, people can come, a chemist that doesn't know much about, these things. So that's one thing. There's a salad bar of experiments also. This is a laser facility with many experiments. So when you going to the experiments, you look at 1, 2, 3, and let's say I want to do these 3 experiments to be able to better characterize my molecular system and what I'm interested in. This is second. And the third thing is that you don't need to actually be a laser scientist to be able to do these experiments. So as far as providing the technology, how much more is then individual labs can do. Some of the laser systems are pretty large. There's a petawatt laser, 2 petawatt laser that's currently not available, not widely available. Maybe 1 or 2 labs in the world. And this is going to be available for lasers. Lots of physicists are standing in line for that particular laser system. So it's unlikely that you're going to get access to it. But there are other laser systems that are used for the 100 kilohertz, 300 watt laser system for transient absorption measurement. It's not common at all. People use kilohertz laser systems that limits the signal to noise and what systems they can use. That's why we can do these in situ measurements and very sensitive and very short amount of time. So
I thought the brilliance you're aiming at higher than what's available at any kind of.
Yeah, so I showed you a graph there. So the brilliance was high. And that is that goal. So I took this graph and I put that thing there, the brilliance on that graph. I can go back to this based on the literature data. This is not my field, the high brilliance. I'm only doing transient absorption, but your question is excellent, and I know that its relevance. You are referring to this graph right here, right? So Eli is somewhere here. This is low photon energy, but very high brilliance. So that's something the petawatt 2 petawatt laser will produce. But some experimentalists, when they make attosecond pulses, for example, short light pulses, it's also important the flux. In order to do meaningful sensitive experiments, and so we can do this 100 kilohertz, attosecond, and so statistically it's good. You can also do that kilohertz, where you need the instant pulse energy has to be higher for certain experiments. So you can do both at this facility.
Thank you.
You're welcome. Next question. Yes, sir.
Can you make subcycle pulses so that the pulse length is smaller than 1 period of oscillation of a wave?
Good question. To terahertz, people worked on that. We don't have that at the facility yet. Single cycle is more possible. Subcycle, I'm sure, this is a laser physics question, so I'm not probably the most qualified person to answer that, but I think, people are working on that, but I don't, it's not my expertise on this. Do you need subcycle pulses?
Or just a colleague of mine was asking.
Yeah. This is a facility, but so most of the people, make the technology possible. Maybe you should write a proposal, your colleague should write a proposal, I want to do this, and I need, to access, to this laser to be able to do this, because I know that this is going to be extremely hard to produce, for sure, that, the subcycle pulses. In the mid-infrared pulses, there's a mid-infrared laser, I think it's called MIR. People working on the the few cycle pulses right now, or the single cycle at the facility. I don't know the status of that, honestly, so I cannot say that. But there are some efforts, to move in that direction.
Okay, thanks.
Yep. Any other questions? Well, thank you very much.
Thank you very much.
Igen,
Okay, thank you very much.
Köszönöm szépen.
Én is köszönöm a lehetőséget. Két nagyon különböző dolg volt, tehát nekem az mentem be valami iséből. Nice to meet you, yeah. And then please talk, yeah.
Yeah, speak to you soon. Bye.
Hi, well, it's Andreas Berger. We're going to meet this afternoon,
Yes.
right?
Okay.
Yeah, so we can talk a little bit more,
Yeah, so you're going to come over and... Okay, so...
I will have over at 1 o'clock. I think there's another person on 1 o'clock.
Okay.
Magnetochemistry is very close
to the where? The CFM?
to here.
To here, yeah, it's 5 minutes walk, yeah, 5 minutes.
So you are here,
Yes.
and then Iena, I'm going to talk to you from Antonio Reeves, hormonal group, at 1:30, I think.
So they are in...
I think that they are in nanogroup.
Oh yeah, that's just... Are they doing biology or...?
Physics of organizational structures and structures and
Okay.
so that's what I have here, but Antonio is had to go to Madrid, or I think he's going to have a baby, the family or something.
The boss of the group is going to have a baby.
Yeah, I think yes, and then the postdoc, Ilenia, probably she's gonna show me the lab. So I will have probably a little bit of time. I can come early. You said that you only have time after 3.
Yeah, actually that fell apart, so I actually do have time. So you're done at 2 with this?
So I have to meet at 1:30.
Yes.
And then, how long that takes after that I can come to your place. That might be a little bit more efficient than waiting.
Yeah, exactly, because in the same corridor.
Let's do that. Then, I'm just gonna
Okay.
walk. If you tell me your office number, I can.
Well, I'm just a corner office. You just can ask the receptionist for me. I'll
Okay,
pick you
then
up.
we'll do that.
Yeah.
Yeah.
So then it's easier than you don't have to go back and forth all the time.
Excellent. Yeah.
So that would be around 2 o'clock, you're saying, Sam?
My guess is 2 to 15 because
okay, that's
the
fine.
postdoc is we're gonna have a half an hour talk.
Yeah, and so I will talk to, I guess you might be interested in discussing some magnetic
Yeah, that
nanoparticles,
would be
even though we don't
fantastic, yeah.
really work with magnetic nanoparticles. And then we can, and when do you need to be back then here?
I don't have to
Or
be
do you
there.
have
You're gonna be
anything?
last on the menu.
So I think we can see if Paulo Vavasori is available as well.
Yeah, we could, anybody who's interested, I'm here to engage with people, so we can talk, and that's my day today. So I know it's gonna be hazy because of I'm in a different time zone.
Yeah.
So that's all.
Yeah, all right. So, yeah, I see you then around 2 to 15.
excellent, yeah.
And then we
I'm
can
looking
have
forward
about
to
an
it,
hour
sir,
or
yeah.
something. I don't know if you want to see the labs. You tell me then how you feel.
I like to look at your labs because you put so much effort in your life into some of these experimental tools, and I mean, why not? Lots of discussions come out from those things. So I like that. Yeah.
Okay, so I'll see you later.
Yeah. See you
Bye.
later. Thank you very much.
Luca, nice
Hi,
to meet you.
Luca. Nice to meet you. We're gonna have a talk right now. Right.
You wanna come? My lab is in chemistry, so just next door here.
I'm gonna pack my laptop.
I'll wait for you.
So,
Hagyom, hogy beszélni.
I saw you with Ryan, but I didn't
Van
want
valaki.
to ask because, well, one of the problems-
Azon gondolkozom, most nagyon gyorsan
Ott van, nem, Luca van. Alex, sorry, I think Alex, hey, you comes first and after you.
All right. Okay, I'll wait for you.
Yeah. Because
How
you
long are you gonna
you
talk?
said 11:30, right, originally?
Whatever. Yeah. So I'll come back here at 11:30. Like
I
Alex.
can say Alex said just take to your office.
All right. Yeah, maybe. Okay.
Yeah, so,
Bring him to my office in chemistry, or just give me a chemistry. Send me a WhatsApp. Okay. Thank you.
István, maradsz a kristályékkal, akkor mert most még lesz egy órát megbeszélés.
Olyan 12-kor elmehetünk enni. De nyilván attól függ, hogy mikor végre.
Alkalmazkodok.
Arra gondoltam, hogy egy menzára menjünk, mert ott gyors